we're going to pull back the curtain on the engine that powers, well, pretty much everything from hyper-realistic gaming to groundbreaking AI. We're going deep inside the modern GPU to really understand its secret weapon, the streaming multiprocessor. Let's dive right in.
So here's the central puzzle, right? A high-end GPU can have tens of thousands of processing cores. Just think about that number. But how on earth do you coordinate all of them without the entire system just grinding to a halt? It's a massive logistics problem, all happening on a microscopic scale. The biggest villain in this whole story is something called latency. I want you to imagine a GPU as this giant factory floor with thousands of workers all ready to go. Well, latency is the time a worker spends just standing around waiting for parts to arrive from the warehouse. And in the world of a GPU, those parts are data from memory. If they're waiting, they're not working, and performance just tanks. And the scale of this problem is just staggering. I mean, if one core has to wait, that's one thing. But what happens when hundreds or even thousands are all waiting for data at the exact same time? Suddenly you have this incredibly powerful, incredibly expensive chip doing absolutely nothing. Just sitting there, twiddling its thumbs. So how do engineers solve this? Well, the solution is a really brilliant piece of architecture, the streaming multiprocessor, or just SM for short. You can think of the SM as a highly organized, totally self-contained workshop inside that bigger GPU factory. Its entire reason for being, its whole purpose, is to make sure nobody is ever idle. It's the engine that's purpose-built to defeat latency. And each of these SMs is an absolute powerhouse of complexity. It's got its own schedulers that act like shop foremen, telling everyone what to do. It's got specialized cores for different kinds of math, its own super fast local memory, and dedicated units just for fetching and storing data. It's basically a miniature computer replicated dozens of times all across the chip. So, if we want to put a more formal definition on it, the SM is the fundamental building block of the GPU. Its job is to manage big groups of computational tasks, which we call threads, and to constantly juggle all of its internal resources to make sure that the time it takes to fetch data from far-off memory becomes completely invisible to the cores that are doing the actual work. Okay, so how does the SM actually pull off this magic trick? How does it make those long, painful delays just disappear? Well, it all comes down to its master strategy, the art of hiding latency. All right, here's the secret sauce. The SM takes 32 threads and bundles them together into a team called a warp. The warp scheduler, that foreman we talked about, is watching dozens of these warps at once. Now, the instant one warp has to stop and wait for data, the scheduler doesn't wait with it. Nope. Bam! It instantly swaps in another warp that is ready to work. This switch is so fast, it's considered to be practically zero cost. And this whole system leads to a really crucial performance metric called occupancy. It's basically just a measure of how many of these warps are loaded up and ready to go inside an SM at any given time. Think of it like a manager having a deep bench of players. High occupancy means the scheduler has a ton of options to choose from, making it way easier to find a warp that's ready to work and, you guessed it, hide those memory delays. Now, getting that high occupancy, it's a very delicate balancing act. An SM's capacity is physically limited. It's like packing a suitcase. You're constrained by the space for registers, the size of the shared memory, and the total number of threads it can keep track of. Your program has to fit within whichever of these three limits is the tightest. You run out of any one of them, and that's it, you're full. And this is a really crucial point, and it's a little counterintuitive. While high occupancy is great for hiding latency, it doesn't automatically mean you get the best performance. See, if your task is just pure number crunching and doesn't wait for memory very much, you might actually get better results by giving a smaller number of threads more resources each, even if that lowers your overall occupancy. It's always a trade-off. Now, you might think everyone does this scheduling thing the same way, but nope. In fact, the two giants of the GPU world, NVIDIA and AMD, they have very different philosophies on how to best tackle this exact problem. NVIDIA, with its whole warp-based system, uses what you could call a hardware-heavy approach. It builds this really complex dynamic hardware right onto the chip. It's called a scoreboard that is constantly tracking which warps are ready to run at any given microsecond. AMD, with its wave fronts, takes a more compiler-driven path. It puts more of the responsibility on the software compiler to organize all the work ahead of time, which in turn can simplify the hardware design. So you've got two completely different paths to the same goal. So far, we've been talking about architecture and philosophy, all pretty high-level stuff. But what does this actually look like down at the level of silicon and electrons? Let's zoom way, way in to the physical reality of these designs. So take a look at this. This is the pipeline for a Tensor Core. These are the specialized little units inside an SM that are absolutely critical for modern AI. For it to do one of its main jobs, a matrix multiplication, data has to flow through all of these different stages. It really is like an assembly line, with each step happening in perfect sequence. And here's the kicker. Even inside this tiny, hyper-specialized unit, latency is still a factor. It takes about 8 clock cycles for a single operation to make its way through that whole pipeline. This just goes to show you that this principle of hiding latency with parallelism, it applies at every single scale, right down to the nitty-gritty. And if you go even deeper, the absolute bedrock of all this math is a circuit called the Fused Multiply Add, or FMA unit. It's built from even smaller, more specialized components. And really, the only way to make these circuits run at billions of cycles per second at gigahertz speeds is to break the math down into a whole bunch of tiny little steps. It's a process called deep pipelining. And all of this brings us to a critical engineering reality. This quote from the research, it really says it all. The register files, that superfast memory that holds the data for all those active warps, they are a massive consumer of physical chip space and power. So the decision to have a large register file to support high occupancy, well, that has huge physical consequences for the final size, the cost, and the power consumption of the entire GPU. So here's the bottom line. The incredibly complex design of the streaming multiprocessor, from its high-level scheduling philosophy all the way down to its transistor-level circuits, is the direct result of a relentless, decades-long engineering battle against latency. That fight is what unlocks the breathtaking performance we now kind of take for granted in gaming and AI. And that leaves us with a fascinating question for the future. As AI models and workloads continue to evolve and get even more complex, which of these two core philosophies is going to prove more effective? Will NVIDIA's hardware-heavy approach continue to dominate, or will AMD's compiler-driven strategy finally find its moment? The answer to that is going to shape the future of computing for all of us.